classical and we are going to look at titrations. Majorly we are going to discuss Karl Fischer titration or method for determining moisture content, representative of a wide variety of high performance modern analytical titration methods, and this is the one that we are going to talk about in this lecture. So thermal methods include thermogravimetry, differential thermal analysis, differential scanning, calorimetry. Analytical titrations. This is a technique that measures concentration of an analyte by the volumetric addition of reagent solution, what we call titrant, that reacts quantitatively with the analyte. So some of the classes of these titrations are acid base, we have redox, we have complexation, and we have precipitation. So for titrations to be analytically useful, the reaction must be generally quantitative, fast, and well behaved. So some of the advantages of analytical titrations: they are greatly flexible, suitable for a wide range of analytes. Then they are manual, simple, excellent precision, and accuracy, readily automated. Some of the disadvantages are that large amount of analyte required, then lack of speciation, calorimetrics is subjective and is sensitive to scale of analyzed, and reagents can be unstable. So these are just some of the titration curves, as you can be able to see. As a strong acid and a strong base, that is the first curve there. Let me just show you that, this one. So if you have a strong acid and strong base, then when we reach here where the pH remains 7, that was what we call equivalence point. Then we have strong base, weak acid. You can see for strong base, weak acid. You can also see that the equivalence point, you can see where it is pointing vis-a-vis this other one. Then titration curve, strong base, polyrhotic acid. So you will see that there is 2 equivalence points when you have a polyrhotic acid. So these are just what we would call the pH and ionization constants. You can be able to see ionization constants. So as we go up, the strength of base is increasing. As we go up, the acid also strength is also increasing. And it is good to note that iodic acid has a very high acidic strength, even greater than hydrofluoric acid. So that one you take note of, nitrous acid and whatever. Then Karl Fischer titration is widely used analytical technique for quantitative analysis of total water content in a material. So some of the applications is in food, the pharmaceuticals, consumer products, or anywhere where water can affect stability of properties. So Karl Fischer, a German chemist, developed a specific reaction for selectively and specifically determining water at low levels. The reaction uses an aqueous system containing excess of sulfur dioxide with a primary alcohol as the solvent and a base as the buffering agent. So you can see the setup, a modern Fischer titrator. So generally the reaction, as you can see the alcohol here, and you'll see sulfur oxide, and then this is, you get an ester. So you can be able to see some of the reagents. 2 molar pyridine in methanol, then here 0.6 molar sulfur 4 oxide, and then we also have iodide. Then endpoint detection by potentiometric detection of iodide ion by a dedicated pair of platinum electrodes. Detector sees a constant current during the titration, sudden drop when endpoint is reached. So iodide disappears and only iodine is around when the reaction finishes. Majorly volumetric Fischer titration recommended for large samples greater than 50 milligrams. So one component titrating agent, one component reagent, iodine, sulfur oxide, imidazole or other base, analyte of known mass added. So 2 components reagents are separated. Titrating agent, we have iodine and methanol. Solvent containing all other reagents used as working media in titration cell. Volumetric Fischer titration, also less recommended for smaller samples less than 50 milligram. So iodine is generated electrochemically via dedicated platinum electrodes, as you can be able to see, where 1 milligram of water is equivalent to 10.72 coulombs. So 2 methods: conventional or fritted cell. Frit separate the anode from the cathode. Then fritless cell, innovative cell design, impossible for iodine to reach cathode and get reduced. So common problems with Fischer titrations: titration solvent, the stoichiometry of the Fischer reaction must be complete and rapid. So solvent must dissolve samples or water may remain trapped. Solvents must not cause interferences. So pH, optimum pH is 4 to 7. Below pH 3, Fischer reaction proceeds slowly. Above pH 8, non-stoichiometric side reactions are significant. So other errors: atmospheric moisture is generally the largest cause of error in routine analysis. So when operated properly, Fischer titrations can yield reproducible water titration values with 2 to 5% weight by weight precision. So example, sodium hydrate usually yield Fischer values in the 15.0 to 16.4 weight by weight range. Common problems with Fischer titrations continued. Aldehydes and ketones form acetols and ketols respectively with normal methanol containing reagents. So water formed in this reaction will then be titrated to give erroneously high water results. with aldehydes and second side reactions can take place, consuming water, which can lead to sample water content being underestimated. Replacing methanol with another solvent can solve the difficulties. So some substances, when now we talk of oven Karl Fischer, some substances only release their water at high temperatures or undergo side reactions in the Karl Fischer media. So the moisture in these substances can be driven off in an oven at 100 degrees Celsius to 300 degrees Celsius. So the moisture is then transformed to the titration cell using the inert gas. So uses of oven Karl Fischer, when you're handling insoluble materials like plastics and inorganics, so compounds that are oxidized by iodine results in anomalous high iodine consumption, leading to an erroneously high water contents. So this includes bicarbonates, carbonates, hydroxides, peroxides, thiosulfates, sulfates, nitrites, metal oxides, boric acid, and iron 3 salts. So thermal analysis. Thermal analysis for determining a specific physical properties of a substance as a function of temperature. In modern practice, the physical properties and temperature are measured and recorded simultaneously. So the temperature is controlled in a predefined manner. So just some classification methods which measure absolute properties. For example, mass is handled with TGA, thermogravimetric analysis. Methods which measure the difference in some properties between the sample and reference are handled with differential thermogravimetric analysis. So methods which measure the rate at which a property is changing is also going to be handled with the calorimetric thermogravimetric analysis. So the concept is sample is loaded onto a accurate balance and it is heated at a control rate, while its mass is monitored and recorded. So the results show the temperature at which the mass of the sample changes. So selected application in determining the presence and quantity of hydrated water, determining oxygen content, and studying decomposition. So these are just examples of a thermogravimetric analysis system. Component there is a sensitive analytical balance. Then we have a furnace, we have a purge gas system, and a computer. Just majorly that is the component. Application of thermogravimetric analysis. We look at composition, we look at moisture content, we have a solvent content, additives, polymer content, filler content, dehydration, carboxylation, oxidation, decomposition can be combined with mass spectrometry or infrared spectrometry to identify gases evolved. So you can be able to see sample temperature, sample weight. So if you are having this is calcium carbonate, hydrated calcium carbonate, when it is heated, we find that at one point it is breaking down to calcium carbonate, and you also have some gases, and then at another point it is now calcium carbon dioxide and calcium oxide. So that is what is being measured. So for example, TGA of a pharmaceutical, so you can be able to see how the mass is changing. We have the green line showing the mass changes. So you can be able to see that. So differential thermogravimetric thermal analysis. So the concept is the sample and the reference material are heated at a constant rate while their temperatures are carefully monitored. Whenever the sample undergoes a phase transition, including decomposition, the temperature of the sample and reference material will differ. At a phase transition, a material absorbs heat without its temperature changing. So useful for determining the presence and temperatures at which phase transition occur, and whether or not a phase transition is exothermic or endothermic. So this is just an example. Sample atmosphere, then we have a furnace, cooling jacket, sample cell, heat shield, and what furnace heater leads. So this is a schematic of a typical instrument of differential thermal analysis. So general principle, change in enthalpy, endothermic reaction minus temperature of sample lags behind temperature of reference. So if you want to know if it is endothermic, you find that temperature of sample lags behind temperature of reference. Then if it is exothermic, temperature of sample exceeds that of reference. So application of differential thermal analysis, we look at glass transitions, crystallization, melting, oxidation, decomposition, and phase transitions. So you can be able to see schematic differential thermogram showing types of changes encountered with polymetric materials. So glass transition you can see here, then we have crystallization, we have melting, we have oxidation, and we have decomposition. So endothermic reactions: fusion, vaporization, sublimation, absorption, dehydration, reduction, decomposition occurs. For exothermic reaction, we find adsorption, crystallization, oxidation, polymerization, and catalytic reactions. So we have differential scanning, calorimetry. So analogous to differential thermal analysis, but the heat input to sample and reference is varied in order to maintain both at a constant temperature. So key distinction: in differential scanning calorimetry, differences in energy are measured. In differential thermal analysis, differences in temperature are measured. Very important. So differential scanning calorimetry is far easier to use routinely on a quantitative basis and has become the most widely used method for thermal analysis, because we just measure difference in energy. So differential scanning calorimetry, the instrumentation are two common methods. We have the power compensated differential scanning calorimetry, where temperature of sample and reference are kept equal while both temperatures are increased linearly. Heat flux differential scanning calorimetry, the difference in heat flow into the sample stroke reference is measured while the sample temperature is changed at a constant rate. So you can be able to see just an example of differential scanning calorimetry instrumentation. So this is just the modern heat flux differential scanning calorimetry. So heat flow in differential scanning calorimetry, as you can be able to see, so endothermic and that is exothermic, and then remember that temperature is being held constant and then increased linearly. So heat divided by time is what gives us the heat, what we call heat flow. So temperature increase divided by time give us what we call heat rate. So this is just step by step differential scanning calorimetry, where we can be able to see some of these processes as they occur. So you can be able to see, crystallization, melting, glass transition. You can be able to see all of them. Then application of differential scanning calorimetry, usually carried out in linear increasing temperature scan mode, but can do isothermal experiments. So in linear scan mode, differential scanning calorimetry provide melting point data for crystalline organic compounds and glass transition for polymers. So easily used for detection of bound crystalline water molecules on solvents, and measures the enthalpy of phase changes and decomposition. So differential scanning calorimetry is useful in studies of polymorphism in organic molecular crystalline compounds, for example pharmaceutical, explosives, food products. So example data from two enantiotropic polymorphs you can be able to see. And then differential scanning calorimetry of pharmaceutical hydrate, can be able to see also loss of water. Then we have melt, then we have decomposition. You can be able to see all that. Then we have modulated differential scanning calorimetry, applies sinusoidal heating rate modulation on top of a linear heating rate in order to measure the heat flow that respond to the changing heating rate via Fourier transform. You know how Fourier transform is a very powerful tool. So this is generally how the modulation occurs. This is the formula, and then so that is it. Then total heat flow you can be able to see here, and reverse heat capacity for glass transition. Thank you so much for listening. You can read more in the Scooge pages 707 to 708. Thank you so much.